Derating of conductors within a conduit is a critical aspect of electrical installation, ensuring safety and preventing overheating. The National Electrical Code, or NEC, mandates derating when the number of current-carrying conductors exceeds a certain threshold within a single conduit. This threshold is generally 3 or more current-carrying conductors. The primary reason for derating is to mitigate the heat generated by these conductors. When multiple conductors are bundled together in a confined space like a conduit, the heat produced by each conductor can accumulate, raising the overall temperature within the conduit. This elevated temperature can degrade the insulation of the conductors, potentially leading to short circuits, ground faults, or even fires. Derating reduces the allowable ampacity of the conductors, effectively limiting the amount of current they can carry, thereby reducing heat generation. In a multiwire circuit, the determination of current-carrying conductors for derating purposes can sometimes be confusing, particularly when dealing with neutral conductors. A multiwire branch circuit is a circuit consisting of 2 or more ungrounded conductors having a voltage between them, and a grounded conductor having equal voltage between it and each ungrounded conductor of the circuit, which is connected to the neutral or grounded conductor of the system. Multiwire circuits are commonly used to provide both 120 volts and 240 volts from a single panel, or 120 volts from each of the 2 ungrounded legs sharing the same neutral. In the case of single-phase lighting circuits operating at 115/230 volts, each multiwire circuit typically consists of 2 hot wires and 1 neutral wire. If there are 2 such multiwire circuits within a single conduit, this would result in a total of 4 hot wires and 2 neutral wires, totaling 6 wires. However, not all of these wires are necessarily counted as current-carrying conductors for derating purposes. The neutral conductor in a multiwire circuit is only considered a current-carrying conductor if it carries significant current. Under normal balance conditions, the neutral conductor in a single-phase multiwire circuit only carries the imbalance between the loads connected to the 2 hot wires. If the loads are perfectly balanced, the neutral conductor will carry no current. However, in reality, loads are rarely perfectly balanced, and the neutral conductor will typically carry some amount of current. If the majority of the load consists of nonlinear loads, the neutral conductor shall be considered a current-carrying conductor. Nonlinear loads introduce harmonic currents into the electrical system, and these harmonic currents can significantly increase the current flowing through the neutral conductor. In particular, third harmonic currents and multiple serve are additive in the neutral conductor of a 3-phase system, and can potentially overload the neutral conductor if it is not properly sized. For single-phase circuits, the effect is less pronounced, but the presence of nonlinear loads can still increase the neutral current. For example, electronic devices such as computers, LED lighting, and electronic ballasts can introduce harmonic current into the electrical system. If these types of loads are prevalent on the multiwire circuits, the neutral conductor should be considered a current-carrying conductor for derating purposes. Another instance where the neutral is considered a current-carrying conductor is when a single neutral is used for parallel conductors. When parallel conductors are used, all current-carrying circuit conductors are counted when applying the provisions of 310.15(2). A. The grounded neutral conductor of a 3-wire circuit connected to a 3-phase, 4-wire Y-connected system is considered a current-carrying conductor. In the scenario presented, with 2 multi-wire circuits supplying single-phase lighting at 115/230 volts, we must determine how many of the 6 wires are counted for derating purposes. Assuming that the lighting loads are primarily linear loads and that there is no significant imbalance between the circuits, the neutral conductors would not be considered current-carrying conductors. In this case, only the 4 hot wires would be counted as current-carrying conductors. Since there are 4 current-carrying conductors in the conduit, derating would be required according to the NEC. The specific derating factor would depend on the type of conductors, the ambient temperature, and the number of current-carrying conductors. The NEC provides tables that specify the allowable ampacity of conductors based on these factors. To determine the appropriate derating factor, the electrician would consult these tables and apply the necessary adjustments to the allowable ampacity of the conductors. The Derating factor is applied to the allowable ampacity of the conductors as specified in NEC Table 310.15 B1. For example, if the allowable ampacity of a conductor is 30 amps and the derating factor is 80%, the derated ampacity of the conductor would be 24 amps. This means that the conductor can only carry a maximum of 24 amps without exceeding its temperature rating. It is important to note that the NEC requires that the conductors be sized based on the derated ampacity, not the original allowable ampacity. This ensures that the conductors are adequately sized to handle the expected load current without overheating. In addition to the number of current-carrying conductors, other factors can also affect the ampacity of conductors. These factors include the ambient temperature, the type of insulation, and the presence of other heat-generating equipment in the vicinity. The NEC provides guidelines for adjusting the ampacity of conductors based on these factors. For example, if the ambient temperature is higher than the temperature rating of a conductor, the ampacity of the conductor must be reduced. Similarly, if the conductor is located near other heat-generating equipment, the ampacity of the conductor must be reduced. The NEC also specifies the minimum size of conductors for various applications. These minimum sizes are based on the expected load current and the voltage drop in the circuit. The voltage drop in a circuit is the reduction in voltage that occurs as current flows through the conductors. Excessive voltage drop can cause equipment to malfunction and can also reduce the efficiency of the electrical system. The NEC limits the allowable voltage drop in branch circuits and feeders. To minimize voltage drop, it is important to use conductors that are large enough to carry the expected load current without excessive voltage drop. In summary, derating of conductors in a conduit is a critical aspect of electrical installation, ensuring safety and preventing overheating. The NEC mandates derating when the number of current-carrying conductors exceeds a certain threshold within a single conduit. The neutral conductor in a multiwire circuit is only considered a current-carrying conductor if it carries significant current, such as in the case of nonlinear loads or significant imbalance between the circuits. The specific derating factor depends on the type of conductors, the ambient temperature, and the number of current-carrying conductors. The NEC provides tables and guidelines for determining the appropriate derating factor and for sizing conductors based on the derated ampacity. Consideration must also be given to minimizing voltage drop. In this specific scenario with two multiwire circuits supplying single-phase lighting, if the loads are primarily linear in balance, the correct answer is 4, as only the 4 hot wires are counted for derating purposes. However, if the loads are nonlinear or significantly unbalanced, the neutral conductors may also need to be counted, resulting in a higher number of current-carrying conductors. Always consult the latest edition of the NEC and relevant local codes and regulations to ensure compliance with all applicable requirements. Remember that electrical work can be dangerous and should only be performed by qualified and licensed electricians. In addition to the general principles outlined above, there are some specific considerations that may apply to multiwire branch circuits. A multiwire branch circuit is defined in Article 100 of the National Electrical Code, or NEC, as a circuit consisting of two or more ungrounded conductors that have a voltage between them, and a grounded conductor that has equal voltage between it and each ungrounded conductor of the circuit and that is connected to the neutral or grounded conductor of the system. Multiwire branch circuits are often used to provide both 120 volts and 240 volts in residential and commercial buildings. For example, a 120/240 volt multiwire branch circuit may consist of two 120 volt hot wires and a shared neutral wire. The hot wires are connected to opposite phases of the electrical system, so the voltage between them is 240 volts. The neutral wire provides a return path for current from both hot wires. One of the key benefits of multiwire branch circuits is that they can reduce the amount of wiring required in a building. By sharing a single neutral wire between two or more hot wires, the total number of conductors can be reduced. This can save on material costs and labor costs. However, multi-wire branch circuits also have some potential drawbacks. One of the main concerns is the potential for overloading the neutral wire. If the loads on the hot wires are not balanced, the neutral wire may carry more current than it is designed to handle. This can lead to overheating and potentially a fire. To prevent overloading the neutral wire, it is important to ensure that the loads on the hot wires are balanced as much as possible. This can be achieved by distributing the loads evenly between the hot wires. It is also important to use a neutral wire that is sized appropriately for the expected load. The NEC provides guidelines for sizing neutral wires in multi-wire branch circuits. In general, the neutral wire should be sized to carry the maximum unbalanced load that is expected to occur on the circuit. In addition to overloading the neutral wire, another potential concern with multi-wire branch circuits is the risk of electric shock. If the neutral wire is disconnected, the voltage on the hot wires may become unbalanced. This can create a dangerous situation if someone comes into contact with the hot wire. To prevent electric shock, it is important to ensure that the neutral wire is securely connected and that all electrical work is performed by qualified personnel. When working with multi-wire branch circuits, it is important to follow all applicable safety precautions. This includes wearing appropriate personal protective equipment, such as gloves and eye protection. It is also important to de-energize the circuit before performing any work on it. This can be done by turning off the circuit breaker that supplies power to the circuit. Before working on a multi-wire branch circuit, it is also important to verify that the circuit is properly grounded. Grounding provides a path for fault current to flow back to the source, which helps to protect against electric shock. The grounding system should be tested regularly to ensure that it is functioning properly. When installing multi-wire branch circuits, it is important to follow all applicable codes and standards. This includes the National Electrical Code, or NEC, as well as any local codes and regulations. The NEC provides detailed requirements for the installation of multi-wire branch circuits, including the sizing of conductors, the protection of circuits, and the grounding of systems. By following these requirements, it is possible to ensure that multi-wire branch circuits are installed safely and reliably. In addition to the safety aspects, there are also some practical considerations to keep in mind when working with multi-wire branch circuits. One important consideration is the identification of the conductors. In a multi-wire branch circuit, it is important to be able to distinguish between the hot wires and the neutral wire. This can be done by using different colors of insulation on the conductors. The NEC requires that the neutral wire be identified by a white or grey color. The hot wires can be any other color except for green or bare. Another practical consideration is the termination of the conductors. In a multi-wire branch circuit, it is important to terminate the conductors properly. This means making sure that the connections are tight and that the conductors are properly insulated. Poorly terminated connections can lead to overheating and potentially a fire. To ensure proper termination, it is important to use the correct type of connectors and to follow the manufacturer's instructions. It is also important to inspect the connections regularly to make sure that they are still tight. In summary, multi-wire branch circuits can be a useful way to reduce the amount of wiring required in a building. However, it is important to understand the potential drawbacks of multi-wire branch circuits and to follow all applicable safety precautions when working with them. By following these guidelines, it is possible to install and maintain multi-wire branch circuits safely and reliably. When dealing with electrical circuits and wiring, it is crucial to always prioritize safety and adhere to the National Electrical Code, or NEC, and local regulations. These codes and regulations are in place to protect people and property from electrical hazards. If you are not a qualified electrician, it is best to consult with a professional for any electrical work. Working with electricity can be dangerous, and it is important to have the knowledge and skills necessary to perform the work safely. This is particularly important when dealing with more complex circuits like multi-wire branch circuits. If you are a qualified electrician, it is still important to stay up to date on the latest codes and standards. The NEC is updated every 3 years, and it is important to be aware of any changes that may affect your work. You can stay up to date on the NEC by attending training courses, reading industry publications, and consulting with other professionals. By staying informed and following all applicable safety precautions, you can help to ensure that electrical work is performed safely and reliably. Furthermore, remember that the information provided here is for general educational purposes and should not be considered a substitute for professional advice. Every electrical installation is unique, and it is important to consult with a qualified electrician to determine the best approach for your specific situation. There are many factors that can affect the design and installation of electrical circuits, including the type of building, the type of loads, and the local environmental conditions. A qualified electrician can assess these factors and provide you with the best possible solution.